The next polymer is polyurethane. From the image, you can easily guess that these materials are commonly used in the sofa cushion and bed cushion, and also kitchen utensils cleaning sponge. The polyurethane. Polyurethane, if you see the main functional group and the linkage group, OCONH. OCONH. For amides, generally you see only this CONH. Addition to the amides is another oxygen is linked. Polyurethane is a class of synthetic resin type, fibrous type, elastomeric type materials and compounds, and comes under the category of organic polymers. So how do we synthesize? We synthesize the polymer by taking two monomers. One is diisocyanates, it's organic compound, and another compound is hydroxy substituted compound. First, in 1937, Otto Baer, he is from Germany. He synthesized this polymer, polyurethane. This is the preparation. What are the two monomers? One is this diisocyanate. So that why diisocyanate, isocyanate, and isocyanate. There should be a bracket here. So diisocyanate will react with a dihydroxy compound. So what happens? So this is the product. We need to have this functional groups. This is the functional group reason for the polyurethane. If you see the reactions, it's very simple. This hydrogen migration is taking place. These hydrogens, see R2 and O, R2 and O, that one hydrogen is moved to the NH. See R2, O, O, CO, NH. Similarly, the other hydrogen will move to this nitrogen. So R1, NH, CO. This is polyurethane. Okay. So now I'll read the theory. The polyurethanes are made by exothermic reactions. That means you need to have two monomers and you have to heat the reaction. You have to heat the reaction. Okay. Between alcohols with the two or more reactive hydroxy groups, and also isocyanates. There are two isocyanates present in another monomer. Monomer 1, this is monomer 1, this is monomer 2. What is the type of reactions? It is a condensation reaction. It is a condensation reactions. We end up with the polymer, that is polyurethane. The group formed by the reaction between the two molecules is known as urethane link. What is urethane link? OCONH. Sorry, OCONH. So before that also there were a few more attempts by Adolf Woods in the year 1848 and Karl Heinz Hensel in the year 1884. They tried to prepare this polyurethane starting with this oxyl chloride. This is phosphine. And amine or NH2. When these two react, we know that it is a base, and nitrogen has a lone pair. This lone pair will undergo a coordinative bond towards the COCl, and then there is elimination of byproduct hydrochloric acid. You can see here RNCO. See here RNCO. There is a double bond. 2HCl will be eliminated. And in 1937, O2 Bayer started with the diisocyanate and taken the alcohol and he did the reaction. So what is the reaction? Taken O2, taken toluene, and he did the nitration. So nitrating mixture is nitric acid and sulfuric acid. This mixture will produce the nitronium ion that will be substituted at the ortho and para portion. For the toluene, for the CH3 phenyl, this is ortho position, this is ortho position. So ortho dinitration plus water molecule. Okay. Again, so the methane, when it is treated with water, we get the carbon monoxide plus hydrogen. And these two, after reactions, we end up with COCl2, that is phosgene. Okay. Parallelly, this nitro should be reduced to amine by some reducing agents. Maybe tin HCl also will work. Also, sodium borohydrate also will work well. Both will work well. Okay. So the nitrous getting reduced to amine and methane will give us COCl2. Both will react. We end up with diisocyanate. Why diisocyanate? Here one isocyanate, here one isocyanate. So we call it as a diisocyanate. Now this diisocyanate will react with the alcohol. We end up with the polyurethane. Okay, that is the way of preparing the material. And properties, has wide varieties of properties. So wide range of hardness. That is the classification of hardness for polyurethane relies on the pre-polymers molecular structure. So based on the molecular structure, the hardness will be framed. Okay, more the branches, more the cross links, or more the polar groups will undergo the reactions, more will be the hardness. High load bearing capacity. Polyurethane has a high load capacity in both tension and compression. Polyurethane may undergo a change in shape under a heavy load, but will return to the original shape once the load is removed with a little compression set in the material when designed properly for a given application. Abrasion impact resistance. For applications where severe wear prove challenging, polyurethanes are an ideal solution even at low temperature. Flexibility. Polyurethanes perform very well when used in high flux fatigue applications. Fatigue is a mechanical property. Flexural properties can be isolated, allowing for very good elongation and also recovery properties. Another important property is resistance to water, oil and grease. This is very, very important in terms of mechanical properties. Polyurethanes material will remain stable in water, oil or grease. So for subsea applications also these polyurethane materials are very much useful. Third one is strong bonding properties. Polyurethane bonds to a wide range of materials during the manufacturing process. These materials include other plastics, metals and wood. This property makes polyurethane an ideal material for wheels, rollers and inserts. Other applications. Polyurethane is the most widely used polymers in industries and many applications. It is one can easily manipulate the applications by tuning the substitutions. Instead of R, if you replace the R as aliphatic to aromatic, the properties will be enhanced. We use it in coating, insulation, different types of foams, textiles, footwears, and many other applications as they used in different percentage. In windmill also, that windmill blades are made up of polyurethanes. the higher at density. Polyurethane also can be used to capture the oil when it is added to the water systems. When you have oil water systems, with this sponge we can capture the oil very easily. This polyurethane is also can be used as a composite materials because it is this if you compress it with many number of sheets, the quality of the material, the hardness, the stiffness will be higher. That will be used for heavy load applications. And the Spider-Man, we all know this Spider-Man. Okay, the Spider-Man wears the dress that is made up of polyurethane. And next one is inorganic polymers. From the name, you can easily understand inorganic polymers. Okay, so inorganic polymer means so the polymers that has a metal ion. Okay, the best example is silicon. Okay, it's known for preparing the inorganic polymers. You can see here silicon will undergo 4 coordinations O, 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 O. Okay, and boron also is very important. Phosphorus also very important for the preparation of inorganic polymers. The silicon gun we use for you can see that in the next slide. Okay, so not only silicon, even germanium also can be used for the preparation of these inorganic polymers. Okay. Sometimes for different applications, we can also use inorganic and organic hybrid materials for different applications. See here, silicon is placed here, phosphorus, nitrogen. Okay, silicon with R substituted one. So based on our applications, we can make different materials. So inorganic polymers containing organic portions attached to the inorganic elements in their backbone. Next one is a rubber. Rubbers are nothing but there are three types of rubbers: natural rubbers, semi-synthetic rubbers, and synthetic rubbers. Rubber is a material which can stretch and shrink. It is a polymer. So the point is that all polymers are plastics, but all rubbers are not plastics, are not polymers. So it can be produced from natural resources. Natural rubber, so natural rubber can be prepared from a latex rubber trees. In South India, in Kerala, you could see a lot of rubber trees. The latex, that's nothing but a milky liquid present in the latex vessels or in the cells of rubber production plants. So the liquid, that's a milky liquid coming from the tree that is having 30 to 40% rubber particles and 55 to 60% water and small amounts of protein is there and steroid glycosides, resins, ash and sugar is present in the rubber, natural rubber. Application of natural rubber. So it is mainly used in the automobile industries as automobile tires. In heavy vehicle duty tires, a major portion of the rubber is NR. It's nitrile rubber. The vulcanization is nothing but, suppose you see the image, this is the natural rubber, raw rubber. So some limitations present in the natural rubber can be improved by vulcanization process. What is vulcanization? Suppose we have two linear chains are there. When you add sulfur into it, sulfur is a yellow powder that will give us a interconnectivity between the two linear chains. This is one chain and this is another chain. Sulfur will be placed in between and it will bridge the two linear chains. So due to that, what happens? A lot of properties, physical properties and chemical properties will be enhanced. So generally the tires that we use it for automobiles are nothing but this vulcanized rubbers. That means we get the natural rubber, we treat with the sulfur powder, we end up with this synthetic vulcanized rubbers. Because of the vulcanization process, the mechanical properties of the material is highly increased. So this is the chemical reaction. This is isoprene. You need to have the heating, you need to have a solvent, you need to have a peroxide catalyst. You end up with a polymer. Here what is the reaction is that this double bond which has two electrons, one will go here, one will go here. Okay. This double bond which has two electrons, okay. So one will go to this carbon, another one will go to this carbon. So because of the two radicals on the adjacent carbons, that will make a bond. So the double bond will convert it into single bond, and single bond will convert it into a double bond. Okay. So the electrons which is reside at the corner carbon will be free now. This carbon which has that free radical, this is also very active. That will undergo further reactions. Another monomer is coming from these directions. That will react with this radical. It makes a covalent bond. If some other polymer comes from this side, that will make a bond with this carbon radical. It makes a bond, some covalent bond. Like that, chain will be propagated. You can see here, double bond is migrated. Remember one thing, in polyisoprene is a unsaturated polymer because it has a double bond. Okay, that's very important. It's 2-methyl butadiene. This is polyisoprene. Remember one thing, polyisoprene also has three types. One is isotactic, syndiotactic, and adactic. There are other sources of trees, plant trees, which is used for the preparation of natural rubber. This kutabacha, his name is Alacium gutta, and rubber fig, Ficus elastica, banana rubber tree, that is Castella elastica, spurges, Euphoria spa, common dandelion, Taraxum finale, Russian tantalum. These are all some plant names. From there also we can get this rubber milk. This is the common tree we see it in India, that mainly Kerala, Hevea brasilinus. Properties of natural rubber. It is reactive towards oxidation. It's a low melting point, low tensile strength. Too rigid when cool, too soft and sticky when hot. Insoluble in water, acid and alkali. You can see the structure here. This is the free rubber or natural rubber. When you stretch it, it will be like this. When the stretch is removed, it will regain its original shape. That is called as elastomer properties, elastic limit. And if it is not returning to the original shape, that is called as plasticity. That means the rubber is getting fragmented. That means you imagine you take a rubber band, give you a stress at both ends, you stretch it to some extent, that length will be enhanced. After you leave the stress, that will, if it regains its original shape, that is called as elasticity. If it is not regaining its original shape, if it is undergoing some deformation, that is called as plasticity. Take a polythene sheets and with the finger just you hold it and stretch it, it won't regain its shape. Okay, like a rubber band. So that is called as plasticity. Synthetic rubber. Why synthetic rubber is important? The mechanical properties, the weak mechanical properties present in the natural rubber will be enhanced if you convert into if you follow the synthetic procedure to overcome those properties. Synthetic rubbers are complex chemical compounds formed through the polymerization of monomers. Typical monomers used for protection feed materials including butadiene, styrene, isoprene, chloroprene, acrylonitrile, ethylene, and propylene. Synthetic rubber protection starts with the refining process of oil, coal, or other hydrocarbons with naphtha as one of the desired product. This naphtha, if you take a petroleum that is a raw material, food product, if you heat that material at different temperatures, we end up with the different products. Among those products, naphtha is one. The other products are diesel, petrol, wax, okay. So many other materials are there. Application of synthetic rubbers. It's used in toys, tires, okay, pipes, rubber pipes, hand gloves, shoes. Next one is synthetic rubber, that is a neoprene. Neoprene, only one change is there. Instead of natural rubber, we have methyl here. In synthetic rubber, we have Cl is here. So monomer is chloroprene or 2-chloro-1,3-butadiene. When it polymerizes, we get the polymer that is neoprene. That means the double bond will migrate to the next position. The double bond will migrate here. The double bond will migrate here. Okay, so you get a single bond there. Once this bond migrates, and this bonds move here, then this bond will get converted into a double bond. This is chloroprene, this is neoprene. Properties are given here. This is synthetic rubber. It is produced by the polymerization of chloroprene. It has good chemical stability. It's very important. This can withstand a high temperature. Means if any chemicals we treat with this, it is highly stable. It is flexible over a wide range of temperature range. It is colorless. Resistance to sun, climate, and ozone deterioration. Recycling. Recycling, we use waste burying techniques and incineration. What is incineration? You take the plastics, put it in a chamber, and just burn it in the presence of oxygen. So all the materials will be converted into, it will char into charcoal materials. Some brands do recycling process using old neoprene to create shoes, t-shirts, etc. It is also used as laptop sleeves, wetsuits, small boats, and boots. Styrene betadiene rubber, SBR rubber, is nothing but styrene betadiene rubber. It is a condensation polymers where we use two different monomers. One is styrene, other one is betadiene. So what happens is that it will undergo a condensation. You end up with this product. The double bond will migrate here. Okay, and this bond will break. It will go here. It will come here. So here it will be a radical species, and these two radicals will combine. You get a bond. this styrene butadiene rubber. Read the theory now. Styrene butadiene rubber derived from the copolymerization of styrene and butadiene. What is copolymerization? Two different monomers. Styrene content in the range of 10 to 25%, and butadiene in it is composed approximately to 60 to 70%. This is the structure of polymer. This table will give us an idea about the comparison between the natural rubber, vulcanized rubber, and synthetic rubber. Natural rubber, it has low tensile strength, that is 20 gram per cm square, whereas vulcanized rubber has higher tensile strength, and the strength is 200 kg per centimeter, whereas the synthetic rubber has much higher tensile strength, that is 250 kilogram per cm cube. So the temperature range, the withstanding range is 10 to 60 degrees Celsius for this material. Whereas for the vulcanized rubber, it is 40 to 150 degrees Celsius. It is high resistance to heat. Tackiness. Tackiness means that is stickiness. It is high tackiness, and tackiness will be reduced if you go from natural to vulcanized one and to synthetic one. Almost zero tackiness for the synthetic rubber. So poor abrasion and higher abrasion resistance, much more higher resistance. The nature is soft and weak. It is stronger. It is strongest. Just now I explained about it. Comparison. These are some images of these plastics. Advantages of this material. It has higher durability, environmental friendly, and for water treatment this can be used, and sound absorber, fire and burn resistance, and soft. SBR has two major types. One is emulsion SBR, other one is solution SBR. Emulsion SBR is abbreviated as ESBR. Solution SBR is abbreviated as SSBR. Okay. This hot SBR or cold SBR are called as emulsion SBR. It can be produced by free radical emulsion polymerization of styrene and butadiene either at 50 to 60 degrees Celsius, a hot emulsion SBR, or at about 5 degrees C, this cold emulsion SBR. Solution SBR is produced by termination-free anionic solution polymerization of styrene and butadiene with alkyl lithium initiator, that is the catalyst. And what is the solvent? Hexane or cyclohexane. It is the solution polymerization reactions. Uses of SBR. SBR can be used in the protection of tires, particularly car tires and lightweight vehicles. So remember one thing, why we have to go for copolymers? Because the weakness of natural rubber can be enhanced by this reacting with another monomer, that is styrene. It's also used in lighter duty tires. It has a lot of industrial applications as belting, insulation for wire, cabling, hull of pads, roll coverings, hoses, gaskets, and seals. SPR is included in shoe soles, cardboard packing and adhesives, and in molded rubber goods. Nitrile butadiene rubber is called as in short form NBR. Here, instead of in SPR, we use butadiene and styrene. Here, instead of styrene, we use this nitrile monomer, that is a vinyl nitrile. Okay, so how to do the reactions? It's addition polymerization. Heat these two monomers at certain temperature, and solvent and free radical initiators will give us this polymer. It also has another names Bunoyne rubber, erboviran, acrylonitrile butadiene rubber. Applications. This can withstand extreme temperatures. This is in automobile industries, useful for gaskets, oil seals, O-rings, and engine hoses. Used to make the rows in the printing industry that spread inks. Used in textiles to waterproof fabric and improve the finishes. Nitrile gloves can range from heavy-duty gloves, footwears, floor mats, sponges, and a host of molded goods. Silicon rubber. This is coming under the category of inorganic rubber, where silicon is bonded to four oxygen atom in a tetrahedral way. Silicon rubber is the most commonly used synthetic rubber or polymer. Similar bond structures are found in the glass, sand, and quartz. It's composed of silicon, which itself is a polymer, together with the hydrogen, carbon, and oxygen. Made from a cross-linked polymer that is reinforced with silica. Applications of silicon rubber: electronics, insulating tabs, sealant, varnish, lubricants, and keyboards and housings. Aerospace silicon rubber is used in spacesuit fabrics, tooling materials, seals, and gaskets. Construction uses silicon rubber for adhesives, sealants, and coatings. Consumer material include anti-stick, backware, food containers, utensils, toys, and jewelry. Medical silicon rubber can be found in tubing, adhesives, and deformers.